We have the article Kinematic Calculation of Flat Mechanism, article 8.7 of the book Mechanical System Calculations of the Marine Facilities. We have the exercise, they assigned the mechanism shown on the figure. 8.7.1, the mechanism consists of the two wheels. One wheel is rolling over the support, and we have the connecting rod with two hinges B and C and the slider here. This is the assigned data, the velocity of the motion of the horizontal velocity 1.4 meter of the motion point A rightward, and the acceleration of the point A meter per second. Yeah, we have to another one direction is meter per second. We have h 1.8 meter per second per square second. The radius is 0.5 meter r1, and the radius, the big radius is r1 is equal 0.8 meters. The length of this one connecting rod BC, we have 1.6. So it is assigned to find the velocities and accelerations of the points B and C and the accelerations of the point A. So what is the sequence or definition of the velocities and acceleration of the flat mechanism? The angular velocity of a link equals to, so we have to find the angular velocity of the two wheels, omega 1. We divided by AP, so this is instantaneous center of the velocities, and VA divided by the AP. AP is assigned as the radius R1 is equal, and the total by the ratio is equal to 2.8 seconds minus fourth degree. 2.8 radians per second is angular velocity, omega 1. Next, we can find the velocity of the point B. This is for the same instantaneous center of the velocity, which is the product of the BP. BP is equal 0.8 plus 0.5 in the brackets here by the omega of the rotation around the instantaneous center of the velocities, and we have the VB equal to 3.624 meter per second. The angular velocity of the link number 2 is 0 because the extreme points of B and C goes to the same direction, the rightward. So we have the velocity of the points equal to velocity of the point B, the same as 3.624 meter per second. And the direction, this moves by the circle, but relative to the instantaneous center of the velocity, this moves directly to the right. The angular acceleration of link A. So we have we consider that mechanism consisting of two links. So the first link is two wheels. The angular acceleration of this one, of course, the wheel is the 1 divided by R1. This is R1. This is the size from A to P. Multiplied by the derivative of the velocity, the first velocity, we have the assigned acceleration, the velocity derivative divided by the r equal to 3.6 second minus second degree. Yeah, this is the velocity, the angular acceleration, epsilon 1, directed to the left, counterclockwise, you can see here. Because we have the acceleration directed leftward, A, this acceleration directed. Tangential acceleration of the point B during rotation of the link 1. Link 1, I mean, there's two wheels. Two wheels is a link 1. It's rotational acceleration relative to the point A equals equals BA. BA is from B to A. Multiplied by the angular acceleration epsilon 1 is relative to the point. So all accelerations we can find as acceleration definite one point of the pole, and I mean linear accelerations, and the relative acceleration of definite one point. We have two accelerations, the tangential and the normal in the motion of the point B relative to the point A. So we have the size BA, R1 is equal multiplied by epsilon 1, and this is equal to 2.88 meters per square second. The acceleration BA tangential. Normal acceleration of the point B and the rotation of link relative to the point A equals. So we have the angular velocity equals BA, this relative as well acceleration, multiplied by squared angular velocity of the wheel, this normal acceleration. the radius by the squared velocity. The tangential acceleration is the radius by the angular velocity. This by squared angle, excuse me, for the tangential acceleration, the radius by the angular acceleration, the normal acceleration, the radius by the squared angular velocity. So we have 6.272 meter per second. To find the acceleration projections on the point B, the vector of time with sum is used. So we have the acceleration of the point A plus the relative tangential acceleration point B relative to the point A, and the normal acceleration of the point B relative to point A. So the projection of acceleration of the point B onto the coordinate axis plane we can find as the projection of the acceleration is because it moves the point B. Actually, it moves by the horizontal. The tangent is line is to the trajectory is horizontal line. So now this projections of the acceleration of the point B onto the coordinate axis we can find as we consider only the tangential acceleration having the AB on projection of the horizontal axis X. So we can find as the difference of the acceleration of the point A and the relative acceleration of the point B tangential relative to the point A. This tangential as well horizontal. So the axis X horizontal, tangential acceleration horizontal. So we have 4.68 minus. This is directed on the left, and the by equal to minus the projection on the ordinate axis. This is only the component of the normal accelerations. 6 is one acceleration or normal acceleration of the point B relative to the point A. Okay, the magnitude of the resulting acceleration of the point B square root of two squared components is the one is on the abscissa axis, and ordinate axis squared components. We have 7.83 meter per square second. Translational acceleration of the point C, the slider, is determined considering the vector sum. So we have the vector sum. So if we have the acceleration of the point B, so the acceleration of the point C equal to acceleration of the point B plus the relative accelerations of the point, the normal and acceleration. Excuse me. This is tangential acceleration. This is angle alpha, and this is one is normal acceleration of the point B, point C relative to the point B. These two relative accelerations of point C relative to the point B. Okay. The angular velocity of this one link is 0 because outermost points B and C of this link move to parallel. Indefinite one instant moment of time. We have the motion of the slider C and the motion of the point B of the wheel. Point B moves horizontally definitely for the instantaneous velocity is horizontal and instantaneous, and this velocity not instantaneous but all time the point C is horizontal. So this connecting rod moves translationally with not the rotation. So the angular velocity of this link is equal to 0 instantaneous angular velocity. That's why the normal acceleration of the point C during the rotation of link 2 relative to the point B is 0 because of the size of the link is twice the maximum size of the link 1. I mean that the link, we say the link is the radius. Okay, this size is twice maximum of the link 1. It's twice bigger. The link 2, so okay. Link 2 since link 1, so the BC equal to 2 multiplied by radius and the first radius. Then the angle between link 2 and the direction of the moment of the slider of the point C at the angle is 30 degrees. The angle, this one angle is 30 degrees. This one angle is 30 degrees. Okay. Let me look a little bit again. Okay, yeah. So we have BC, this point B, BC is 1 and 6, R1, this radius is just only 0.8. So this diagonal hypotenuse is twice more than this one leg. Okay, this is what we told about. And those the alpha angle of the inclination of the instantaneous angle of the inclination of the connecting rod is 30 degrees to the horizontal. The projection of the acceleration of the point C to the y-axis is the relative acceleration point B, the projection on the ordinate axis minus tangential acceleration multiplied by the cosine alpha. Tangential relative acceleration of the point C relative to the point B. And this is projections on the ordinate axis, and the alpha tangential acceleration of the point C relative point B. We can find those have the acceleration of the point B, and the relative acceleration tangential of the point C relative point B is as acceleration of the point B projection on the ordinate axis divided by cosine of the angle of the inclination of the connecting rod to the horizontal axis. Then we have by this proportion 7.24 meter per square second, and the total acceleration magnitude of the point C of the link, the slider, equals, we say the link, wheel, connecting rod, the sliders. Each element of the mechanical system we indicate here in this definite one assignment as the link. This equals as the acceleration of the point B projection of horizontal axis multiplied by the tangential acceleration of the point CB by sine alpha. And we have this as minus 1.06 meters per square second. The angular acceleration of the link 2 thus is equal this acceleration of the tangential, the point C, this tangential acceleration of the point C, 7.24 divided by the BC, this BC, the size of the connecting rod, and equal 4.53. Questions and comments. A plane movement of the mechanism and its links, the elements of mechanical system, the translational movement, the instantaneous velocity center, the angular velocities of links, translational velocity of the points. They just remind that we have to know the considered concepts. The plane movement is a movement of the mechanism, is a movement if all points on the mechanism moves in parallel to the definite fixed plane. The translational moment is with not rotation, the instantaneous velocity center, the point velocity which is equal to 0, the angular velocities of links is definite, finding of definite points relative motion. We can divide by the radius, and we can find the angular velocity, translational velocities of the points. Translational velocities as the just movement with not so we have the translational velocities of all points, and we have rotational velocities of the bodies we can consider as the links of the elements of the mechanical system. H72 tangential acceleration, normal acceleration, angular acceleration. Angular acceleration we can find as a tangential divided by the radius. Tangential we can find accordingly if we know radius and the angular acceleration by the product. Nominal acceleration, this is a nominal, excuse me, this is normal acceleration. Normal acceleration is the depend on the angular velocity, and is equal to the normal acceleration by the product of the radius by squared normal, excuse me, the squared angular velocity divided by the radius. Acceleration of the point moving relative to another point, the pole corresponding to the sum of the acceleration of the pole and the acceleration of the point. Acceleration of the point moving relative to another. Yeah, when we consider the mechanism and we have definite mechanical body, and we have information about the angular acceleration and the angular velocity of the mechanical body, and we have the translational acceleration of any point of the body, we can find the translational acceleration and components of all points of the mechanical body having these three indexes. we have to know the radius between the pole and the point of the which for we have to find the acceleration. So let me remind that this normal acceleration is product of radius by divided by the radius squared, velocity angular divided by the radius, I told. Okay, thank you.